Hello, my name is Lars Schubert and I would like to give you now a practical overview about the structural health monitoring methods we use. Let's start here. That's a part of a wind turbine rotor blade, and I would like to demonstrate the acoustic emission technique on this type of wind turbine rotor blade. What you can see here are different transducers. They are now attached and mounted to this structure here. Now, as you learned during the theoretical part, the transducers have the task to listen inside the structure in a frequency range between 10 kHz and 500 kHz, sometimes in some specific steel structures up to 1 MHz, and they listen for acoustic emission signals. And now I'm going to hit the structure here with my artificial impact, and as you can see here in this localization part and software, I see the acoustic emissions which arrive at different positions wherever I hit the structure. And if you do now this acoustic emission monitoring approach over a specific time, over weeks or months or even years, then you have a clear insight or you have a clear view inside your structure where you have zones of damages or not. Okay, let's now move forward to the active approach. I would like to demonstrate the active approach on this part of pipeline here. We attached 3 transducers, 1 in the middle, 2 in the end, and the specific on this structure is that we reduce the wall thickness. In practical, this is done by abrasion effects, so we have a medium inside which reduces our wall thickness, and the customer is interested in the residual wall thickness of, in this example here, of the pipeline. So we can send now acoustic waves from one transducer to another one just by pushing this button, and the system calculates a residual wall thickness of 7.4 millimeter, and in this case for the thinner part of the pipe it calculates 5.9 millimeter. But let's have a look inside the system here. So what does the system do? So the system is intelligent because it knows the propagation speed of all acoustic waves inside the steel structure. That's called here dispersion curves. And what the system does is measuring time signals. So I push the button here, you can see the time signal of the thicker part of the pipe, and if I push the button for the thinner part, then the waves behaving like as you can see here. And the system calculates now the propagation speed, and from the knowledge propagation speed to residual wall thickness, the system can calculate the residual wall thickness for your pipeline or for your vessel, for example. If you would like to have a more detailed overview about damage condition like crack in a weld or something like that, or if you have local corrosion, then you have to take more of those piezoelectric transducers, as you can see here on this sensor belt. But this specific sensor belt, my colleague Martin will explain in a few minutes. But let's now concentrate on the system behind the damage localization. I would like to give you an overview about the damage localization on this structure here. That's a pressure vessel. The firefighters use pressure vessel, and also cars are using pressure vessel for storage of liquid gas, for example. We have here attached our piezoelectric sensors behind this T3, T8, T7 and so on, and we have a model of the geometry inside our localization software here. And what I do now, I attach an artificial damage that's like, it's this one, and I attach it on a position like here, and now I will start a measurement. And what happens now? Every piezoelectric disc is sending waves from one point to another. But the propagation will change on this specific point as I attached here those artificial damage. And the software now takes all the signal and calculates the position of the damage. And this takes, as you can see, some seconds, and then you can see, okay, there's a difference or there's a change in the propagation path between transducer 8 and transducer 7. And if we look behind our signals, we can also see that T8 to T7 shows differences in the blue signals, which was the baseline, the new condition, and the red, which was the older condition after I attached this damage here. And here in that case, we just attach the sensors to the surface, but we can also integrate the sensors inside the CFRP structure and make it ready for the use, for the commercial use. Okay, that's all I want to show you in the moment for the methods. Now let's go inside the building here or the room to my colleague Martin.
Hi, I'm Martin Oemus. I'm part of the group Systems for Condition Monitoring, and today I have the pleasure to guide you through our lab and show you some of our measurement systems. Here's the first exhibit. It's a small part of an old rotor blade of a wind turbine, which we used to test our acoustic emission sensors, of which you can see one particular example here. It's assembled on the outside, which admittedly doesn't make too much sense. That's why let's have a look inside. You can see how the rotor blade is made. You have on the outside and on the inside glass fiber, and here you have some joints where the parts are glued together. So of course, if the wind comes, there's a lot of stress going against the whole structure. And sometimes tiny micro cracks can happen. Actually, they happen all the time. And we assemble our sensors on the inside at different positions to listen very closely to when and where those cracks happen. By taking the runtimes of those cracks into consideration, we then can extrapolate the position of the cracks, and once the number of crack and noise events at the same location exceeded a certain threshold, we can raise an alarm flag to the operator of the structure, so he sends someone to investigate before, well, the turbine stops working or worse, something breaks, which could be dangerous. Now, it's probably a bit abstract to imagine the whole acoustic thing and where it all goes, so we prepared something so you can see for yourself. Let's say that's the glass fiber surface of the rotor blade again. We have 1, 2, 3, 4 sensors, and we have a crack event. And you can see that's the acoustic waves. They are picked up by the sensors. They measure the runtime, they communicate, and voila, they know where the crack happened. It's pretty accurate, certainly for a structure as big as that. Yes, so much about acoustic emission. Something else very exciting to show you, and that's our sensor belt. And it's, here. That's a tube, a pipe-like structure. It can be a small pipe, can be a large pipe, and we attach our sensor belt to it, which consists of several small pieces. So first there's the central processing unit, which does all the number crunching and the analysis of the data. Of course, it needs to communicate with somebody who operates it. Or, I mean, it can also be done in a monitoring fashion. It uses Wi-Fi. It also works underwater, surprisingly well. And it needs power, so we have a coil to remotely supplied. Here's the power supply unit. And let's say it's operated underwater and we have a remotely operated vehicle coming close to it. It then needs to dock. And maybe you can hear the sound. When I come closer, there's a high-pitched noise, and voila, we have energy. And it starts communicating and measuring. Now, to do measurements using acoustic waves, we also need transducers, and you can see them here. That's a share wave piezo transducer. It's tuned for a specific wavelength and the share wave mode. So if it's underwater, the water would damp out of plane waves, so we use the share wave mode, which also has the advantages of not dispersing, so it's the guys from analysis are happy about that. And one other thing is, we have 1, 2, 3, quite many small modules. They're cheap to manufacture because they only consist of the transducer and the preamplifier electronics. And even if it's a pipe as large as the room, we can just stick them together and we have a larger sensor belt. How does the error detection work? So we configure one of those nodes as the transmitter. Then the wave goes to a crack. What cracks can that be? Actually anything. It can be a crack like this. It can be corrosion where the pipe became thin. It can be sediment where the pipe became thicker than originally. There are actually pipes made of carbon fiber composite. They suffer from delaminations. We can detect that. And by reflecting the wave, it goes back, and it might be a little bit altered than if there was no crack, which we can then analyze in the central unit and store it, or directly send it back to the remotely operated vehicle for direct analysis. Yes, I think that's most I have to say about that. So if you have any questions, feel free to ask.